So I also want to join the other speakers in thanking the organizers for the very much appreciated invitation to speak at this conference. I'm honored, and also want to thank for the perfect organization and the beautiful and unique location that was chosen to celebrate this anniversary. So the title of my talk is been taken, I borrowed the title from a characteristic paper of Bell that goes back to 1986. Actually, it's the last paper in the famous collection, Speakable and Unspeakable in Quantum Mechanics. And to motivate my talk, I want just to briefly go through the abstract of that paper. And the abstract starts with, I borrowed the title of a characteristic paper by Schrödinger that goes back to 1952. That's real. I mean, Schrödinger gets the credits for the title, Are There Quantum Jumps? So the paper is basically a reflection of Schrödinger on the status of quantum mechanics. At that time, it's a kind of a frustrated reflection because he was, he liked his equation, of course. He thought, like most people in a way or another now think that the wave function gives the complete description of a state of a quantum system, but then there is a problem. There is that the wave function spreads out in space, that gets highly entangled in a very short amount of time. So you have soon you have a very crazy state, according to the Schrödinger equation, in particular due to the linearity of the Schrödinger equation, and then you have to understand how to get the world as we know it out of it, how to get particles out of that, how to get the defined trajectories for particles, as you see in bubble chambers, for example, how to get in general definite outcomes. It's a measurement problem. He didn't like that, so he didn't like quantum jumps because they were not part of the equation, they were not part of the dynamics. And so, as Bell noted, this is the problem that Schrödinger had back in 1935 with the cat paradox. It's basically the same story. Then Bell goes on and says that for him, at least, there are, with the way out, there are two possibilities. Either the wave function is not everything, or it is not right. So with the wave function is not everything is basically what Einstein also thought, the incompleteness of quantum mechanics. There is more than the wave function in describing reality. There are additional degrees of freedom, what people now technically call hidden variables. They don't necessarily have to be hidden, but there are additional variables. And that's an interesting research program. The de Broglie-Bohm theory is such an example where you have particles, point-like particles in the simplest way to formulate a theory that move along trajectories. So there is no problem about superpositions because the reality of the description of nature is not in the wave function. The description of nature is at the position of the particles that move, and the role of the wave function is to guide the motion of the particles. So linearity wouldn't be a problem in that sense. But this talk is not about Bohmian mechanics. This talk is about the other alternative that Bell takes into account. The wave function is not right in the sense that the equation that the wave function is solution of is not exactly the Schrödinger equation. It's something different. And actually, this is apart from collapse models, because basically this is what I'm going to talk about. This is an interesting question. Is the Schrödinger equation right or wrong? Of course, we know it's wrong in some sense. You have to replace with a Dirac equation. You have to do quantum field theory. But in the rest of my talk, with Schrödinger equation, I mean the essence of quantum mechanics, which is the linearity of the Schrödinger equation, the unitarity, the superposition principle. Is that true or not? That the nature goes in like that? Of course, so far, all experimental evidence is compatible with this assumption that nature is linear and wave function superimposed, but it doesn't have to be like that forever. So this is the line I will follow here. So the rest of the paper of Bell is about collapse models, and also the rest of my talk. So what is the idea behind this spontaneous wave function collapse? You modify the Schrödinger equation. You add additional stochastic and nonlinear terms in such a way that you are capable of describing a smooth transition from a quantum world where you have this wavy behavior, the wave function diffuses, it breaks, it recombines, you have interference effects as you see in the experiments, and the classical world where this doesn't happen. Wave function is always localized in space, so well localized that it behaves for all practical purposes like a point. So you have always a wave function, but the wave function is localized and it's basically point-like. And actually, there is, the equation is ugly in a way, the equation I will show you in the next slide, but there is some beauty in that because you have in a single dynamical framework, you can explain these two opposite, apparently contradictory behaviors. They are not. They are just two different situations that happen at different scale. At some scale, you have a wavy behavior, but at another scale, the macroscopic scale, you have a point-like behavior within one single dynamical framework. So that down there, you can see the original, I mean, it's probably one of the most relevant works in the field by Girardi, Riemann, and Weber. 1986 is the same year of the Bell paper I started with. And of course, the contribution is from many other people. Philip Pearl in the US. We have here Nicolas Gizen, Lajos Diósi, Stephen Adler. I mean, I don't want to make the full list of people. So that's the equation of collapse model. I mean, in general equation, there is one way to write it. It's not the most general, but I mean, it captures the general structure with you have the unitary part and the linear part with the Hamiltonian of the system, and then you have the collapse terms. And I want to make a comment about that. So if you ask the question, how can I modify the Schrödinger equation? Again, with modification, I don't mean to add a weird potential, to modify the structure, so to change the linearity of the equation. How can you do that? So mathematically speaking, you can do it anyway. I mean, when you have a linear thing, you need to add the nonlinearity. I mean, just pick one nonlinearity and you have a nonlinear equation. But actually, that is not the case in quantum mechanics. It's something that we learn over the years. And again, I thank Nicolas because he was the one that one of that more than others understood what was going on. You cannot do what you want. So if you want to add nonlinear terms, you have to be careful, otherwise your theory is immediately inconsistent. You can do superluminal signaling instantaneously between faraway systems. Linearity, nonlinearity must come together in a very balanced way with stochastic terms. Otherwise, the theory becomes inconsistent. And basically, the balance is so delicate that this is, in some sense, the unique structure. So people speak of collapse models in the plural because there are different models, there are different ways in which you can put things there, different operators, different coupling constants, but the structure has always to be the same. It's that of a continuous quantum measurement for those of you that know of it. So in that sense, you can claim, perhaps in a bit of a bold way, but you can claim that collapse models are the alternative, or this kind of dynamics is the alternative to the unitary and linear dynamics given by the Schrödinger equation or by quantum mechanics. So it becomes interesting to see what it says and how you can test it. Okay, so, again, so you have these new terms. Typically, you can collapse in any basis, but since you want to explain why we are localized here in space, everybody considers collapse models that collapse in position. And so the operators are function of the position operator in a way or another. And so that basically, so that there is a noise. So the noise is W of t. So this is a Wiener process. It is white in time. Why is it white in time? Simply because the equations become nicer. Otherwise, they are uglier. But I will come back. So it's an important issue, the Markovianity of the dynamics. There is a correlation function. There is a correlation in space. It's G of x minus y. It's a correlator. And that's basically what distinguishes between different models. And basically, that's it. There are not messy. There are other degrees of freedom, but that's more or less the story. The important point, as I mentioned before, is this amplification mechanism. You can fix uniquely the red part of the dynamics. So the Hamiltonian depends on the system. You can, so M, the operator M is in this case is the mass density operator because for many reasons it would be the most natural choice, but there are other choices actually. So you can fix the red part of the equation in such a way that what I said before happens. If you take one atom, 2 atoms, 10 atoms, the red part of the equation, the effect is negligible. You have just the unitary part, the linear part, and so atoms can live in a superposition of more states, can be highly delocalized in space, and so on and so forth. But when you have a composite macroscopic system, so like, again, the Schrödinger cat, since we are talking about that in this session in a way or another, then the collapse effect becomes strong. So strong that you cannot even start creating a superposition that these terms prevent you from doing that. You have a classical system that behaves in a classical way. The interesting thing is that also that if you apply this equation to a measurement situation, when you have a microsystem coupled to a macro object, you recover, for all practical purposes, the phenomenology of quantum measurements as it's usually presented in textbooks. And that's actually one of the goals of the dynamical reduction program. That would be also one of the goals of Bohmian mechanics, if you wish, of all these realists attempt to reformulate, reinterpret, or rewrite quantum mechanics. The goal is that you can describe what happens during the measurement. That would be something. So it's not that the measurement is something external to the theory that tells you what happens. Measurement is part of the theory. Measurement is just something that happens dynamically, that has to obey some equations. And then you solve the equations, and you can decide what happens and why that happened during a measurement. So I think this is a nice feature of these models. I mean, not only these models. Okay, so. And that's, you modify the Schrodinger equation, no? The red part of the story. So you're modifying slightly in a suitable way the dynamics, and so you're making predictions that differ from standard quantum mechanical predictions. So, I mean, it becomes interesting to test these models to see whether there is some truth. And actually, from my point of view, this is the real interest in, I mean, one of the main interests in these models. They challenge the superposition principle. They challenge the building block of quantum mechanics. And if the superposition principle is will be verified in the next 100 years, wonderful. Quantum mechanics, the range of validity of quantum mechanics has been extended. If the superposition principle fails, well, it will be even more exciting, I think. Surprises are more exciting than confirming what we know. And I think that the best service you can do to a theory is to challenge it. So that's what collapse models are also about, and also I'm happy about all the experiments that we heard about in creating larger and larger macroscopic quantum superposition. So that's the state of the art. So you can, of course, the obvious way, the direct way, and the most difficult, but in the same time most exciting way is to do interferometric experiments. You heard from Marcus Hart, Max Aspelmayer, Gwen now, and Michel also before mentioned about that. What do you want to do? You would like to do, ideally, I'm a theoretical physicist, so for me it's easy to create a superposition. You take a system which is as massive as possible in a delocalized state, which is as delocalized as possible for a time which is as long as possible, and then in a protected environment, of course, you want everything, and then you check whether you have the superposition or not. If you have the superposition, then you have linearity, the quantum theory is correct. If you don't see the superposition, then things becomes interesting, because you have to ask yourself why you don't see the superposition. Perhaps the experiment was not good enough, was not done in a careful way, or perhaps something interesting is going on. So, okay, so this is the direct way of doing that. But they are difficult, these experiments. I've seen in particular from the talk of Marcus Aspelmayer, but also from GWN now, that there is always a trade-off. You increase the mass, you decrease the delocalization distance, and that's frustrating. You were saying GWN, but I mean, that's part of the game, no? Life is not easy in many ways, and also for experimentalists, for theoreticians, life is easier. And it will come one day, but still, I mean, there are many challenges to do that. So something that we have been working on, and there is also some lessons about that, are non-interferometric experiments. It was the eating effect that Juan mentioned before. So the non-interferometric experiments, which are based on the fact that when you collapse the wave function in space, you can do the similar argument for other variables, but we are interested in space. When you localize in position, you unavoidably shake the system. It's not possible that you have a superposition here and there. You just kill one term and you keep the other one as it is. You always shake the system, something that we proved recently, I will come back on that. So in a very strong sense, there is a noise associated to the collapse of the wave function. So its effect in all collapse models, there is the noise, but you can say something stronger to that. They have to be like that. They not just happen to be like that. They have to be like that. And so you can devise a new strategy for testing these models. Instead of having to deal with delocalized or in general quantum states, to control quantum states and see whether they persist, they are preserved over time, you can do a completely classical type of experiment. You just look at the motion of a part of a system. Could be microscopic, macroscopic. You just have to monitor the motion of the system in a very accurate way, because this noise it's a faint noise. So this is the advantage. The disadvantage is that, of course, it is an indirect test of the superposition principle, and also it is also model dependent. The noise is always there, but the strength of the noise depends on the type of model. It's again, typically you would use a white noise, because the theory, the mathematics is much easier, but white noises are an idealization. They don't exist in nature. Okay, and so I will tell you what happened when you apply this idea to testing some of the collapse models. So this is a Dioschi-Penrose model. So the equation was considered by Dioschi back in the late 80s. It was not written in that way. Would be a more modern way of rewriting the equation, but the essence is the same as in the paper by Dioschi. You see that's the equation I showed you before. What is specified and what qualifies this model is the correlation function, which is capital G over H bar and 1 over R, which enters in the integrals. And then later, some years later, Penrose also considered the idea that gravity can cause the collapse of the wave function. So I don't want to go into the argument, but the bottom line is that, I'm trying to understand him the best I can, is that in the true quantum theory of gravity, in the correct quantum theory of gravity as he has in mind, superpositions of different space-times are unstable and should decay, and the decay depends on how massive, let's say, how energetic is such a superposition. So when you have two masses in a superposition, you generate two superposition of different space-time curvature, and then this should be unstable over time. Of course, it doesn't have the theory, that would be beautiful, but so it tries to do some phenomenology at the non-relativistic level, the simplest and the first thing you would do. So by using the time and energy uncertainty relation, the lifetime is estimated to be h bar over E, where E is the gravitational content of the superposition, morally, as if you consider when you have a superposition here plus there, you consider it as half here and half there in some sense. You compute the Newtonian potential, and that gives you the energy. But the interesting thing that Penrose notes is that if you apply this formula with an atom in a superposition here and there, you get that the lifetime is extremely long, so this instability is completely negligible. When you consider basically a macroscopic object, the opposite happens. The lifetime is very short. The instability causes a fast collapse. So without adding, there is this idea, but no new parameters. It's just gravity that, in this sense, would justify classicality. So it's a very appealing idea. Okay, so one technical thing which is important for the following discussion is that, of course, when you have a 1 over R function inside an integral, things diverge. That would mean that the lifetime would be 0. The collapse would be instantaneous, also for an electron, so the model cannot work. But there is no surprise about that. This is a non-relativistic model. You cannot, ask too much from such a model. So that you have to have a cutoff, a short range or high momentum cutoff in the integral. Penrose and Dioschi take two different attitudes towards this cutoff. For Penrose, the system, the geometry, the physics of the system, if you wish, defines the cutoff, and there is a recipe. I don't want to go through that now. That would take too much time. But the cutoff is system dependent. For Dioschi, instead, this is a parameter, universal phenomenological parameter, that should be constrained by experimental evidence. That's what we did in a paper that appeared not many years ago. So this is one example of a non-interferometric experiment. It's a radiation emission experiment. Why radiation emission? Because there is a noise. If the noise shakes matter, and matter is made of protons and electrons, the noise shakes protons and electrons, and they are charged particles, and so they would emit radiation. So the one prediction of these models is that there is some faint radiation coming from all of us, from matter everywhere, because the noise sources gives the energy to emit these photons. Of course, the rate is negligible, it's very faint, very small, completely negligible in standard situation. But if you do a dedicated experiment in an underground facility in a very protected environment, then you can say something. So this is the theory part of the analysis, something that we did in our group. So this is the emission rate, the number of photons per unit time and unit frequency that should come out from matter. So you see many constants. You see R0 in the denominator because the R0 is in the denominator because the smaller R0, the smaller the cutoff, or vice versa, the higher components in momentum you are taking into account, and so the larger, the greater the emission rate. And then N N is the number of atoms, so it's the size of the system. The more matter you have, the more photons you should see around. Of course, the formula looks simple because there are many approximations, and it's valid. So it's valid in a specific range of frequencies. So the experimental part comes. So this was, of course, I mean, they didn't build the experiment for us. The experiment is a dark matter experiment, so we just piggybacked it. We use the experiment for our purposes. And it's a germanium detector. There is the schematics. It's in the Gran Sasso facility, so you see the inside of it. And that's the data taken. This is part of the spectrum. It's been cut on the left. The red, the black histograms are the counts, the number of counts over 2 months, more or less. And then the green histogram are the simulated counts. So I mean, the detector I've learned is it's not something where nothing happens. There are always some radioactivity, and so you get always some signal, even if there is nothing from the outside stimulating the system. And so you know that you expect a certain number of counts, which are the green one, and basically you see that the leftover is about 70 over 2 months. So not many counts are unexplained. They are unexplained either because the characterization of the detector was not perfect, or because there is a new physics. So that new physics, since it's a dark matter detector, it would be a dark matter signal, but it was not the case. Or it could be, I mean, in principle, it could be a collapse signal. But since the 70 counts over 2 months is not much, that means that the strength of the collapse from the DP model cannot be too high. And so we set a bound, a lower bound, which is the green region with the green line that you see in the one-dimensional parameter space of the model, while the blue and the red refer to previous results in the literature. The important point is the red bullet, which was the value of R0 that would apply to that system according to the prescription of Penrose, which is excluded. So, and that's the claim that also made this, went in the news somehow, so that we excluded the DP model, the Yoshi-Penrose model, experimentally. But there are 2 important comments about that. The first one is that, as written in the paper, so it's excluded in the simplest version. That's, I think, I maintain the claim. So it's excluded in the simplest version, but of course, it's always the problem of the noise. You can change the spectrum of the noise. The noise is not white, and then you can evade the bound. But then you can do that, but then you are basically putting some new information, so the spectrum of the noise, and then you have to give a justification for that spectrum. So the model becomes more complicated, or perhaps more interesting, perhaps because really the white noise assumption, that first attempt to write a model, was too naive, and then reality is much richer than that, so we don't know that yet. So the second comment refers to a comment of Penrose regarding this result. He was saying in a very understandable way, what you are proving is that the Yoshi model is not my idea. In my view, I collapse the wave function, but there is no noise, the noise that you are excluding. But then again, I come back to our result, which actually the research behind that result was motivated by this comment of Penrose. In that sense, I claim that is wrong. If you collapse the wave function in a consistent way, you have to accept that you have a noisy behavior. It will not be the noise in this equation, it will be another kind of noise, a very acceptable, but there will be a noise. Otherwise, the model is inconsistent with the framework of quantum mechanics. Okay, the CSL model is the other continuous spontaneous localization, for those who don't know. So it's the other model in the business, together with the DP model. Again, the equation is always the same. The choice is a different correlation function, which is a Gaussian that comes from the original Ghirardi Rimini-Weber model of 1986 I mentioned at the beginning of my talk. So this is another correlation function. Now there are 2 parameters, lambda, the strength of the noise. It is the analog of capital G over H bar in the Yoshi-Penrose model. And then you have RC, the strength, the resolution of the noise. It displays somehow a similar game as R0 in the DP model, or the inverse. Okay, so now the parameter space become 2-dimensional, and this is the parameter space. So the gray region at the bottom corresponds to value value for the parameters lambda and RC, which should make the collapse very weak, so weak that you wouldn't be able to justify the classicality of the world as we see it. So if the world is not classical, then we give up collapse models. So the parameters, the value of the numerical value of the parameters cannot be too low. The collapse cannot be too weak, otherwise the model doesn't pay any service. And so the region is excluded. Of course, the division between the white and the gray region cannot be so sharp because there is a large uncertainty on what is classical and what is not, what you want to make classical and what you don't want. But that gives an indication. At that time, we didn't make the division blurred. We made it sharp, but of course, it is not like that. And the black bullets there refer to guesses about the numerical values of these parameters by GRW originally and by Euler. Okay, so and then the colored region, this one comes from cold atoms, is the excluded region. What experiments are excluding? The exclusion comes from the bottom down, because from the top down, sorry, because at top you have strong values of the parameters for which make the collapse strong. So that's the first thing that you would test, whether the strong values are correct or not. So this is a cold atom experiment. So by the group of Markasevich, we took the data. Of course, they didn't do the experiment for us. They took the data. So they achieved the result of cooling a cloud of cold atoms down to picokelvin, and then if there is a noise, the noise cannot be too strong, because otherwise you don't reach the picokelvin temperature. And so you exclude the upper left region of the parameter space. This is the radiation experiment I mentioned before, and you see there is quite a bit of papers, because this is, from the theoretical point of view, it's a very nice exercise of non-relativistic quantum electrodynamics with a noise. So it's something that is unusual. It's a very, for those that like theoretical physics, for the fun of it also, it was a nice system to study. Okay, so these are gravitational wave detectors. So you see very classical experiments. This is Auriga, LIGO, and LISA Pathfinder. What is the business here? The business here is that in order to see gravitational waves, you have to make the system, the mirrors, very stable. But there is a collapse noise that shakes the system. It shakes the electrons, it shakes the protons, and it shakes the center of mass of the mirror, even if it's a macroscopic mirror. And the level of accuracy in controlling the motion of the mirror in this experiment is so great that you remove that region. And actually, this is one way. For example, you see that LISA Pathfinder is the green region, which covers a larger portion of the parameter space with respect to LIGO. This is one way to see that LISA Pathfinder is more precise as a detector than LIGO. And it had to be like that, because they had to go to space. They had to prove the European space agencies that they will see something to justify the mission. Then these are cantilever experiments, so in the mesoscopic regime, and also updated version. This was the situation in a couple of years ago when we wrote the review, and then just 3 days ago, so these are our pictures. So now the picture changes because I've taken from the preprint that comes out. So then it looks different, but it is similar. This region is the added region, excluded region. Okay, so I'm basically at the end. So with some comments. So what to say about collapse models? Well, I mean, you can read yourself. So the white region is still the region to be explored, and you can also count the orders of magnitude. So it looks small because the picture makes it look small, but it is a large portion. It is. Oh, by the way, let me go back. So the interferometric experiments, I should have put the picture. The interferometric experiments that of Marcus, of GWN, and so on, they would be in the parameter space. They would be up here. They would be somehow. They would cover this area over here, just to give a perspective of interferometric and non-interferometric experiments. Okay, so there is still a long way to go. There is to exclude these models, also because the noise. So if you remove the white noise assumption, you see that some of the bounds vanish, because they strongly depend on the fact that the noise is white. And so what is the moral? The moral is you can see it in two ways. For collapse models, it's still, there are still many experimental exercises to do to decide whether there is truth in that or not. But that's secondary to the main message, which goes against something that I heard it was said before. We are very ignorant about the validity of the superposition principle towards the macroscopic scale. So the superposition principle has been beautifully and exceptionally well tested in the macroscopic and the beginning of the mesoscopic regime. But we do not know whether it holds for very large system and for macroscopic system. And this is something that should encourage funding agencies in funding experimentalists, not theoreticians, to find, but perhaps a little bit also, to find an experimentalist in testing the basic building block of the most important theory that we have. It's like the equivalence principle. We have to decide whether the equivalence principle is right or wrong. If it's wrong, then the framework of general relativity falls apart. But not just the mathematical framework. Our worldview of the picture that emerges from general relativity is wrong. The same with quantum physics. If the superposition principle fails, and we don't know what happens, quantum mechanics will be wrong, and and I'm finished, the words of Tony Leggett was mentioned at the beginning of the talk, something else will take over, something that we cannot even envisage at the moment. Thank you for the attention. So this is my collaborators and funding agencies.
Thank you. We can take a few questions.
Thank you for the talk. One of the problems of the collapse models is that there is no principle behind it. I mean, you think that there is a problem and that you try to fix it, but you don't know at which scale it will fix. Nowadays, we can derive a standard quantum mechanics out of simple principles, and by standard I mean unitary evolution. So we have several sets of axioms starting with Lucian Hardis that give us this formalism. And imagine you are in an island, you think about it, and you're convinced that, well, the world has to follow this theory. What would be the equivalent to that? Or why is my feeling that you don't have the equivalent of that?
The motivation behind collapse models is the measurement problem. That with linearity, you struggle, and then, the debate begins in justifying the world as we see it. And then collapse models are simply an attempt to give an answer to that by assuming that linearity is not a fundamental principle of nature. It's nothing more than that, I would say.
I would allow myself to break the order because I had to turn down your... So your turn, because we turned you down last time. So go ahead, and then we take one more questions from the last mic. And Elisa, hopefully you can speak with Angelo and others in the break.
Great. Thank you. Thank you for the talk. I was just curious, it seems for the most part, for these macroscopic systems, you focus on mechanical systems or massive systems. To what degree can any of these models be tested with electromagnetic systems where we have tremendous control of macroscopic electromagnetic systems?
Yeah, the point is that the photon is very light. So if you make the mass equivalent of the photon, you can question whether the photon should collapse, the wave function of the photon should collapse. But suppose that it does, you would make a mass, or in this case, energy proportional model. And then, so I'm not so much familiar with the state of the art in this kind of experiments, but I suppose that the mass equivalent of the largest macroscopic superposition with photons doesn't beat the experiments of Marcus Hahn, for example. That would be my guess.
Okay. All right. Thank you.
Fantastic. First question from the second mic.
Yes, thank you for the very clear talk. I have a question about the specifics of the details of the model. So you propose that every particle has a certain probability of collapsing at a certain rate and so on. And you mention electrons and you mention protons and neutrons, but somehow we know that these things, or these are theories that we use to model fundamental physics. These particles are not particles, right? They're excitations of the fields. And so is there work to connect just the L2 of R to the N kind of stuff that you use for the collapse models to somehow some collapse of the field modes?
Yeah, so let's say, these models are done in a quantum field theoretical language, so that's not the issue. We worked at the non-relativistic level, so we took the quantum field of a proton, the quantum of a slowly moving proton or a slowly moving neutron, and then because we were interested in the phenomenology and in testing these models. But you could do with the quantum field of a quark. And you have a sort of compoundation invariance in the sense, it's a kind of a technical term, in the sense that if you are not interested in detailed structure of the nucleon, you can treat it as an elementary particle with an effective collapse rate. So that would work like with any theory. So if you are not interested in the details, you can consider it effectively as an elementary particle. But if you wish, you can go down to that level.
Okay, and you can kind of translate from this between these levels. And the thing is also relativistic covariant then?
No, the point, so that is the big issue, which I intentionally left out because there would be another talk. That's the issue that comes with non-locality. So the collapse must be non-local in order to account for the violations of Bell's inequalities, and then the problems come about relativistic covariance.
All right, thank you.
Sure.
Yep. Thank you, Angelo, and thanks everyone from this session. I believe we need to set up for the panel.